In this video, I show you how to find the volume of this wedge of wood that I had to cut out of a tree that was dead in my backyard, a pine tree. So the idea was that for that tree that was standing there, I took a horizontal slice with my chainsaw to about the middle of the tree, and then I took a diagonal slice with my chainsaw, and I meant to meet the other one at the middle of the tree, but I missed. I should have had it about a ½ inch higher. But in the end, we do have a wedge, and in order to find its volume, we don't have any formula from geometry that would help us know exactly how to find that volume. Now, we certainly do need to know a few pieces of information, such as the dimensions of the wedge. So we need to know, for instance, the diameter of the tree, which was 14 inches. We need to know the width of the wedge, which is 6 inches. I meant for it to be 7. Now, by the width of the wedge, I mean from there to here, where the wedge ends. And then we have the maximum thickness of the wedge, which was 3 inches. And by the maximum thickness, I mean the thickness out here. The thickness here, of course, goes down to 0, so the thickness varies by how far into the tree we went. But at the outside of the tree, it was 3 inches. So, how are we going to find this volume? First thing I'll do is trace around the outside here of the wedge so that we can get an idea of the size of the tree. Again, I said its diameter is 14 inches. And the nice thing about setting up a coordinate system in any kind of an applied problem is that we can set our coordinate system wherever we want. And a convenient place to put a coordinate system when you have a circle is to set its origin at the middle of the circle. Because that means that the equation of a circle centered at the origin is x squared plus y squared equals the radius squared. Of course, if the diameter is 14 inches, the radius is 7. So you get 7 squared, or 49 here. Now, in order to make things easier, I'm going to give you, instead of the real wedge at this first video, I'm going to give you the dimensions of the wedge I meant to cut, so that it would go all the way to the middle of the tree, so 7 inches wide, and then maximum thickness would have had to have been an extra ½ inch, 3½ inches. And we will get back to the original wedge later. But here we have then a wedge, and the idea is we need to find its volume. Now, looking at this is just a circle. We could find areas, but that's not what we're interested in. We're interested in a volume. But the same principles will still work. We'll start by trying to figure out how we could slice this and approximate it with finite sums. So if I slice and approximate then here with finite sums, I could slice in much the same way we've done before, say for area between curves. So we have a height and a width, but we have a third dimension to worry about here, thickness. Here's the idea. If you take your wedge, this is more or less like that wedge, and if we are to slice it in the same way that we're doing here, slicing it vertically, then when you take it off, you have this box then with 3 dimensions. It's got not only your width and your height, but also a thickness there to the inside. So the idea then is we need all 3 dimensions in order to find that volume. Now, your width is going to be delta x, just as we had our widths of delta x when we did our rectangles for areas before. Same idea. And then for the height, we would need to find the y-coordinate at the top curve minus the y-coordinate of the bottom curve in the same way we did for our areas between curves. It's the same setup. So I need to know equations of the top and bottom curve. Well, how do I get those? I have this equation, x squared plus y squared is 49. If I simply solve this for y to get plus or minus square root of 49 minus x squared, then that tells me the equations of the top and bottom curves. because remember, positive y coordinates are above the x-axis, so that's this top curve. Y is square root of 49 minus x squared, positive. And negative y coordinates are below the x-axis, so that's the equation of the bottom curve. Y is minus square root of 49 minus x squared. So our heights then are your top curve minus your bottom curve. Minus a minus, of course, makes a plus. So you have one plus another one, or two of those. Twice square root of 49 minus x squared then for your heights of these bars. But now what about the thicknesses? That extra dimension that goes inside. The idea here was that the thickness is greatest, it's 3.5 inches when x is 7, but it's at 0 inches when x is 0. So let's look at a side view. In our side view, we have at an x-coordinate of 0, a thickness of 0 inches, but at an x-coordinate of 7, a thickness of 3.5 or 7/2 inches. So if you give me any x-coordinate, we would need to know what the thickness is at that x-coordinate. Now, how are we going to find that thickness? Similar triangles, right? The ratios are going to be the same because these are similar triangles. So just like 7/2 is half of 7, that would have to be half of x, or x over 2. So that's my thickness. My third dimension is x over 2. That means my volume then is going to be found by multiplying these three together. So I would have my height times my thickness times my width, but that's just one of those boxes, right? Just one of them. So I have to add all those up for all the boxes, so I've got a sum. But just as we've seen before, if we make that a limit of Riemann sums, or an infinite Riemann sum, then we wind up with a definite integral. And so once more, by looking at these finite sums, we're able to come to something that gives us a definite integral. One more application of these definite integrals. So I've got an integral, I'll go ahead and let those 2's cancel, of x times square root of 49 minus x squared dx from 0 to 7. Alright, so that's what we would have to find. Now let me pause to show you the general formula and the general concept of what's going on here. Because our volume was equal to an integral, and I'll go from a to b from left to right, then a product of two things here, because although we have our height here and our thickness here, our widths go away in our integral formula to the dx. So what formula is left in here with that dx? What's left is just the height times the thickness. Now what is that height times the thickness? It's this dimension times that dimension. This times that. In other words, it's this one times that one. It's the area of this part that's the slice, where I cut the slice out there in the middle. It's the cross-sectional area. So our formula then becomes integral of a of x, where that is the cross-sectional area. Now, when we integrate this, because this is square root of not just plain x, we would need to use substitution. We would have u is your 49 minus x squared, etc. And when you go through all the details, you wind up with a volume of 114 and a third. Is that right? Yes, 114 and a third cubic inches. Notice it's cubic inches because it's a volume and we have the 3 dimensions. Alright, and I'll skip those details. Now in our next video, I'll go back to the original wedge and show you how to find its volume.